Okay, welcome back to our discussion of Chapter 11 in the DB2 course. Let's use this video to have a look at the details of external merge sort, the sorting algorithm used by relational database systems when it comes to the sorting of tables of arbitrary size when the available working memory in RAM is limited, when it's really scarce even. Okay, so the typical scenario that we will be facing in such a system is that we are to sort the heap file or the entries in the heap file of some table T. All right, so here we will simply equate the table T and its heap file, right? And well, we assume that this is a large file. It has n pages, and n may be arbitrarily large. If n is small, we will probably be content with using just in-memory quicksort, for example, and then all of this discussion does not apply. So let's assume that n is truly large. N in particular is truly larger than the number of pages of RAM working memory, of buffer memory that we have available in our database system. So B would be such an integer that describes the available working memory inside the buffer of our database system. Of course, B will be much smaller than N if external merge sort, is supposed to play a role here. Okay. What we assume instead is some scratch memory, some working memory that we may use on some external storage, for example, on an HDD or SSD disk. We assume that double the size of n blocks is available on this external working memory. All right, so normally this is no issue. We've got plenty of space on such external disks. Typically more than ample space to hold 2 times the size of any table T. All right, so that would be the memory or the external and internal memory setup that we assume. Now we will discuss external merge sort. That's the sorting algorithm that can operate with really scarce working memory. As we will see, we can do with only 3 pages of working memory available. The algorithm will be slow then, but it will be functional. It will be workable, and it will be able to read an unsorted input file, well, the heap file T, and it will write a sorted output file, sorted according to a criterion that we may specify. Okay, so we can go the way from here to there by using only 3 pages of memory inside our buffer. Even the tiniest buffer should have B equal 3 pages available. Typically, there will be more pages available. B will be larger, and we can benefit from the presence of more internal working memory pages, as you will see later. The external merge sort algorithm will work in a series of passes. So a series of passes will touch the data multiple times, reshape it, massage it, and then write another temporary result that will be then read in the next pass to then maybe compute the final result. The larger B, the more space, the more working memory we have available, the fewer passes we will need, the fewer intermediate temporary results we have to write. These temporary results are called runs, and they are held on disk. And of course, this means writing runs, and reading runs again means disk I/O. And we, of course, would like to reduce that. So the larger B, the fewer such turns, the fewer passes we will need, and the more we benefit. But in the most dire situations where B indeed is only 3, we could even then perform external merge sort. Okay, so let's have a look at one of these passes, one of these iterations of the external merge sort algorithm. As I told you, this would be reading from disk, and it would write to disk. All right, so that would be one pass of the external merge sort algorithm. If this is not the final result, of the algorithm, then we would feed back these just written temporary results into the next path of the algorithm to perform this external merging again. We will have a look at this at the details in a minute, and then write the next temporary result. Maybe this could be the end result of the sorting again. If it's not, then we have to take another pass. So that's the overall global path and iteration structure of this algorithm. All right. So what we assume when the external merge sort algorithm starts is that the input file T, the heap file T, has already been split up in small runs that are already sorted. Okay, so here on the left hand side you can see small runs, small fragments of the original input file T that are already being sorted internally. So if I look inside run 1 here, I will see that the rows inside that run, a fragment of the contents of the heap file of T, that the rows inside run 1 are already sorted according to our sorting criterion. Okay. At the very beginning, you may ask yourself, well, yeah, okay, so much of the sorting has happened already. So when did that happen? So we will clarify how the very start of the algorithm is being performed, so that you can go from an entirely unsorted heap file T into a situation where there are already a number of runs that have been created, and these runs internally are indeed sorted. These runs are indeed small, but together, collectively, they make up the contents of the entire heap file T. This is what I try to indicate here. Okay, so the entire heap file T is actually split up into these light gray runs here. On these light gray runs, we will merge light gray runs to write larger dark gray runs here. As you can see, there is multiple of these runs will be written as the intermediate output of our external merge sort. Of course, if we collectively look at the output of such a merge pass here, then if we collectively look at all of these, then again, we will of course see the entire contents of our heap file T. Nothing is being invented, no rows are being invented, and no rows are being forgotten, of course. Okay, so how does this merging take place? Well, let's assume that indeed we have only 3 pages of working memory available. So B indeed equals 3. Then this would be the contents of our working memory of our buffer. And 2 of the 3 pages would be allocated to read rows from these 2 input runs. Okay, so we are able to allocate 2 or B minus 1 of these pages as being pages to read input into. Okay, so B minus 1 runs will be read, or the first part, maybe the first block only of each of these runs will be read and then moved into working memory. There they are. The third page inside the working memory will be used to hold the merging result of these 2 read pages, okay? Because the input, the contents of these rows are already sorted according to our sorting criteria. It's very easy to perform a merge operation. We will look at the details of that by reading from this and this and this and this page, and to produce a merged result that will also be sorted by the sorting criterion. Whenever this page is full of sorted results, it will be moved over to the output run here on the disk, on the external memory. Okay, so read B-1 blocks from the inputs, have them in the working memory, perform merging on them, right? Whenever the merge result exceeds the third page here, this dark gray page inside working memory, move that page onto or append that page onto the run that we are currently creating here in the working memory. Okay. At one point, all of the pages of our input runs will have been read, all of their contents will have been merged, and then we end up with this output run here. This output run is longer is longer than B input runs. Actually, it's longer by a factor of B minus 1. B minus 1 input runs contribute their contents. All of their contents will be merged. So the output run will have a length of B minus 1 times the input run length. And this is what I indicated down here. So in each of the paths, the length of the runs is increased by a factor of B minus 1. All right. So this is just a legend, so that makes it hopefully easy to interpret this diagram. Input runs, the darker gray merge output runs. This is just the B minus 1 may merge operation. Okay, so if B is 3, we are looking indeed at the two-way merge here in this particular picture. All right. Of course, once runs 1 and 2 have been merged, later on we will merge runs 3 and 4 to obtain this particular intermediate output run. Well, at least 2 such runs are being created in this picture, at least in this path. So we would need another path at least to merge these 2 runs in the final result. Okay, so this is the general idea of the external merge sort. A pseudocode sketch of this entire algorithm is found on the next slide. So that would be a pseudocode sketch of the external merge sort operation. It will operate on heap file T, and the availability of buffer pages, of working memory pages, is just B. Okay, so B has been 3 on the previous slide, but hopefully B is larger. Okay. So, right, so n has been the number of pages in T, we have seen that already. This would be the number of runs that we split our heap file T to in the very beginning. So R is the number of runs that we create in the very first phase of external merge sort. R is 4 in this particular picture, right? So our heap file T has been divided into 4 runs here. Okay, so that would be R. And we determine R by simply dividing n by the buffer size. Why is that? Because this is what we do in the very first pass 0. Let's call it pass 0 in the initial pass of our external sorting algorithm. What we will do is we will split T into R partitions. Okay, each of these partitions will have B pages. Okay, each of these partitions will have B pages. B pages fit into the working memory of our database system. So what we will do is we will read these partitions in turn. Each of these partitions will have B pages. Well, maybe the last partition will have less than B pages. Okay, but each of these partitions will not exceed B pages. So what we can do with each partition, we can simply perform an in-memory sort, maybe a quick sort on these particular partitions. Okay, this is of course an in-memory sort that will be performed according to the sorting criterion that we are after. And once this partition has been sorted, we will call it a run. So this Ri here would be one such run. R, capital R many of such runs are being performed in pass 0 and are placed on the scratch disk or on the working memory disk. It's exactly these runs, R1, R2, R3, R4, that we are looking at in this particular sketch of the algorithm. So this is how we see the entire process, by just performing in-memory sorts on very small partitions that are never larger than B pages in our working buffer. What we end up is these runs Ri. And how many of these? Well, capital R many of these. So if there is more than one of those runs left, then we will start a merging process. And well, since we have B pages available in our working memory, B minus 1 of these pages will be devoted to read input from these input runs. This is what you see here. Okay, So B minus 1 of these B pages will be devoted to input reading. The last page, the Bth page in a sense, will be devoted to hold the merge output. Whenever that page is full, it's being written out to the temporary memory. Since we are performing a B minus 1 way merge here, in this path that we are executing, the number of runs will be reduced by a factor of B minus 1. Okay, so in a two-way merge sort, the number of runs halves in each path. Okay, in a B minus 1 merge sort, the number of runs is divided by B minus 1 in each such path. So that will be the number of runs that we write out to disk in this particular path. And you see, this is exactly what we do here. That many runs will be written. To write each of these runs, we will read B minus 1 runs from our input. Right. So R will be reduced by a factor of B minus 1 in each of these passes. At one point, R will indeed reach the value of 1, and this means a single run is left. This would be the entirely sorted output file that would constitute the output of our external merge sort algorithm. So this indeed would be the single run that is being output in the external merge sort. And as you can see here already, the more pages we have available, the larger B, the faster R will decrease and the less passes we will need. Okay, since each pass involves reading the current input runs from disk, merging them, writing them back out to disk, each savings of a pass is of course very welcome. So increased B may lead to a decrease in the number of passes. This slide indeed shows a summary of the expected number of input and output runs, the expected sizes, and the expected passes that we will need. So I think this should be easily readable. So in the first pass, so after pass 0, when this in-memory sorting has already been performed, so in the first path, when we are already reading the initial runs, then this is the number of runs that we will see in this particular case. So the entire heap file of n pages has been divided into n divided by b runs. So each of these runs has a length of b, which is also shown here in the second column. In the output will have less runs. Indeed, the output will have n divided by b minus 1 runs. So the number of runs decreases by a factor of b minus 1, as we have just discussed. If b is 3, then the number of runs will halve in each of these paths. Okay, but the size of these output runs will of course increase. It will increase by a factor of b minus 1. So if b is 3, then in each of these passes, the runs will double their length. Okay, this would be the output of the first path. And of course, what the output of the first path is indeed the input of the second path. And again, the number of runs will be divided by a factor of b minus 1. So that's what you see here. The run size, the run length, will increase by a factor of b minus 1. That's what you see here in this exponent, in the square exponent. And so it goes on. So what we have written here will be the input to path 3, and so on and so on, until we have reached path n, where the number of runs, or number of output runs, the number of output runs would indeed be only 1. This marks the end of external merge sorting. So if you look at each of these paths, what is involved in reading and writing these temporary runs, then you will see that the number of runs in the input and multiplied by the run size, this will lead to n. Of course, no no row of the input is being forgotten, no other row is being invented. The entire heap file of n pages is split and represented inside these input runs. So n divided by b times b, indeed this is n, or n divided by b b minus 1 square times b minus 1 square, this indeed again is n. So in each of these passes the input has the size n, and likewise the output has size n. That is what is to be expected. The entire input has to be read, to be fed into the merge process. The entire output has to be written to disk, because we have to collect the merge results from the buffer and append them to the output runs. So each of these passes will indeed perform 2 times n I/O operations. If n is large, this adds to a large number of I/O operations. So each path performs this number of I/O operations. So how many passes are there? Well, of course, there would be the pass 0, in which we first split the entire file into initial runs, which are then sorted in memory. But to do that, we have to read the entire heap file, perform the in-memory sorting, and write out the initial sorted output runs. This would be pass 0. This would be one path. How many merge passes will we need? Well, this is the number of runs that we have to merge. We have to reduce this number of runs to 1. In each of the passes, this number of runs is reduced by a factor of b minus 1. So the logarithm to the base of b minus 1 of the number of initial input passes, that would be the number of merge passes. And again, as you can see, if only we could have a larger b here, b larger than 3 hopefully, then of course the number of merge passes will strictly decrease. The number of input runs will decrease, and the number of needed merge passes will decrease as well. Okay, so much for that. Let's have, as the final bit in this video, let's have a look at the implementation of this operation, of the merge operation. We are being presented with a number of input runs here. It's only 2 input runs in this tiny example here, but in general there may be many such input runs. Maybe the input to the merge operation, and this merge operation will pick the correct row from each of these input runs, the smallest row in a sense, and will append this to this output page. Let's have a closer look at how this merge operation can indeed be implemented. So this would be such a depiction, or well, a sketch of this merge operation. Okay, well, we are presented with a number of input runs. Here are the input runs. Okay, let me circle these. If we look inside these input runs, you will see they are indeed sorted already. So what I'm showing here is only the key values of the records that we are trying to sort. You see these integer keys here, they represent an entire row, an entire record that is behind these. Well, only the sorting criterion would be relevant to our discussion here. The rest of the row is just not shown. Okay, so in this case, there is indeed 3 input runs that we are faced with. All 3 of them contribute to our merge operation. Okay, so what we see here, all right, let me circle this. This would be the contents of our working memory, the contents of our buffer. Okay, as I told you, one of the pages in the buffer, this page, would be the output page to which we append all the rows that we have already processed. If this output page is full, we would take it and append it to the current output run on disk. The other b-1 pages would be devoted to reading the input runs. And well, I've organized this input reading here in form of a priority queue. Okay, so I would use b-1 pages of my input of my working memory to be structured in in the form of a priority queue. At the root of this priority queue, I would always find the row that is smallest according to the ordering criterion that is currently being pursued. Okay, so when you see these squares here in the input queue, this is just a very rough depiction of the data structure of this queue. If you see such a square in this sketch, then this means there's an empty slot in the queue that can be filled with another input row. So let's do that. Let's move these read pointers that we will maintain each of the input runs. These read pointers, let's move them forward one step and indeed read the minimal element in each of these input runs. Okay, so the 2, the 1 and the 8 will be placed in the queue here. The 2, the 1 and the 8 have been placed in this priority queue according to the ordering criterion. So indeed, the minimum element 1 is found at the root of this priority queue. You will also see that each of the keys here are being annotated, are being marked so that we can see which input run contributed this particular value. So indeed, this 8 here has been contributed by input run R3. Okay, right. So now it's time to emit our first output row. Of course, it will be the row at the top of the queue here. It will be this one, the one that originally stemmed from the input run 2. This is seen in the next slide, where we trace the merge operation here. Okay, so indeed, it's time to write this one, the minimal one, into the output. Okay, the queue head is placed into the output page here. This leads to an empty slot at the top, at the root of our queue. We know that run 2 is now to contribute its next input row. Okay. And that's it. That's what we do. We will advance the read pointer in run 2. This is the old stage of the read pointer. The new state of the read pointer is indeed this state, where we have moved it to the right one bit. Okay, so this element, this 2 of run 2 is now being placed inside our input queue. We will reorganize the input queue so that the minimum element is being found at the root. There's two entries here in the input queue. We have decided to place the 2 with that stems from input run 1. This is found in the top, in the root node of the queue now. And well, it's time to emit this particular value and append it to the output page. That's what we've done here. There it is. It has been appended. There is this empty slot at the top of the queue already. The empty slot is being filled with the next element of input run 1. Okay, so it's time to move that pointer forward. And that's what you see here in this next picture. The input pointer has moved forward. The 3 has been loaded and placed into the priority queue. Now it would be time to emit the 2 that originally stems from run R2, and so on and so forth. So that would be the implementation of the merge operation. Of course, there is some algorithmic trickery going on because the number of input runs from which we can pick our next element, this could be large. We would, of course, would have to maintain an efficient implementation of this priority queue here and its reorganization and so on. All of this can be super interesting and super tricky. We won't dive into the details here. This level of detail should suffice because there is quite another number of interesting details to be explored when it comes to external merge sort. And these interesting details are being explored in the upcoming video. See you then. Take care. Bye.